In this video, we're going to be doing some practice writing molecular ionic and net ionic equations. A molecular equation is one in which the compounds are written as complete compounds fully together, even though in aqueous solution they might be electrolytes that are actually broken apart. The ionic equation shows them broken apart where any strong electrolyte, that means a soluble ionic compound or a strong acid, are broken apart, and anything that is either insoluble or molecular and not a strong acid stays as the complete compound. And the net ionic then cancels out the spectator ions. So let's look at this first example. Lead nitrate and sodium iodide. So the first thing we need to do is figure out what are going to be the products. Here we have two ionic compounds, both aqueous, reacting in solution. So whenever two ionic aqueous compounds react, basically what's going to happen is they're going to switch partners. So the first compound I have here is lead nitrate. So lead nitrate has two parts here. It's got the cation, which is the positive ion, in this case that's lead, and it's got the anion, which is nitrate. Sodium also has a cation, sodium, and iodide is its cation or anion. So when they switch partners, lead is not going to be interested in sodium because they are both positively charged, and positives to positives will repel. So instead, lead is going to want to go after iodide. So lead will become lead iodide. Instead, it will leave the nitrate behind and switch out for the iodide. Now the second part of this is, well, what is the formula of lead and iodide? We need to balance out the charges in order to figure that out. So lead's a transition metal. We don't know off the top of our head what its charge is, but we can determine its charge by how many nitrates it is combined with. Nitrate is a polyatomic ion with a 1- charge, and if there's two of them, then that must mean this whole thing contributes two negative charges, which means in order to cancel it, lead must contribute two positive charges. Iodide, on the other hand, that's always set as -1. So if lead is two positives and iodine is just one negative, then lead iodide would be written as PbI2. It would take twice as many iodides to cancel out that two positive charge on the lead. Now I'm just going to put a blank space for its state of matter, and we'll figure out its state of matter in a little bit, but let's go ahead and write the second compound. So I've used up lead, I've used up iodide, what's left is my sodium and my nitrate. Now sodium is 1+, nitrate is 1-, so they can go together in a 1-to-1 molar ratio. So simply sodium nitrate, and because there's only one nitrate, I don't need the parentheses around it. Next thing, make sure everything is balanced. So I've got one lead to start with, one lead at the end. That's fine. I have two nitrate ions at the start and only one at the end. So to fix that problem, I'll put a coefficient of 2 out front. Two nitrates, two nitrates. I have one sodium to start with, and now I need two sodiums at the end, so I'm going to put a coefficient of 2 here as well. Two sodiums, two sodiums. Now I also have two iodides at the start and two iodides at the end. So everything's balanced now, and all it took was those two coefficients. Last part, and we're done with our molecular equation, and that's the states of matter. So looking at our solubility tables and our solubility rules, we see that anything containing sodium or anything containing nitrate, regardless of what it's bonded to, is always going to be soluble without any exception. So if this is soluble, its state of matter is going to be aqueous. The second part here is lead iodide. If you look at the solubility rules, you'll see that lead iodide will end up being insoluble. So if this is insoluble, then it is a solid, and this is what we call the precipitant of the solution. It comes out of the solution. So now we have our products, We are balanced, we have states of matter, and we are done with our molecular equation. To write the ionic equation, we're going to take anything that's a strong electrolyte and break it apart into its ions. Now, once everything is separated by itself, everything must have a charge that is not still in a compound, and everything must have its own individual state of matter. It's very important. So, any soluble ionic compound is a strong electrolyte. So, lead nitrate would be a strong electrolyte. It should break apart. Lead, in this case, has a 2 positive charge. So I'm going to write 2 plus. And its state of matter of aqueous will be distributed to it as well. So this is aqueous. Now the next part here is the nitrate. Now this is where students get confused because they want to write NO3 with a subscript of 2. But here's what this really looks like. I have this compound lead nitrate. So let's just illustrate this really quickly here. I have a lead 2 plus ion, and then I have 2 NO3 molecules. That's right, polyatomic ions are actually molecules that have charge. So I've got these 2, put one on one side, NO3 with a minus charge, on the other side, NO3 with a minus charge here. So in the ionic equation, we take these and we break them apart. Break them apart. So there's our lead 2 plus that we got, and then the nitrates, NO3 minus, that are aqueous. I'm going to end up with 2 of them. So how do you write that there's 2 of something in an equation? You don't do it with a subscript, you do it with a coefficient. So that 2 comes out in front. So be very careful in an ionic equation. If you end up with 2 of an ion, then that 2, or whatever the subscript, if you have 3 of them, needs to come out in front and become a coefficient. The only things that get to stay in subscripts are those subscripts that are part of the polyatomic ion. NO3, this 3 is part of that polyatomic ion formula. Those are the only subscripts you get to keep. So with the sodium iodide, sodium is Na+, that is aqueous, and iodine is I-. Now if you do this correctly, you should still be balanced, meaning if I have 2 sodium iodides, then when I break it apart, I should end up with 2 sodium ions and 2 iodide ions, because I had a sodium iodide, and then I had another one of a sodium and an iodide. So once I break everything apart, I should end up with 2 sodiums, so 2 sodiums, and 2 iodides. In the products, the first product that I have is lead iodide. Lead iodide is a solid, so you cannot break apart into ions if you're not even dissolved in solution. So therefore it will not break apart and it will just stay as lead iodide. Nothing about it will change. The sodium nitrate, that will break apart, and same concept from over here where the 2 got distributed when they broke apart. This 2 will also get distributed when they break apart. And do not forget, everything needs a charge when it breaks apart, and everything needs a state of matter once it breaks apart. Notice that I did not write the charges on lead iodide. That's because it did not break apart. You only write the charges on ions when they are broken apart, not part of a compound. You do not write the charges when they are part of a compound because the charges have been canceled out. Now everything should still be balanced. Always double check. 1 lead, 2 nitrate ions, 2 nitrate ions, 2 sodium ions, 2 sodium ions, 2 iodide ions, and 2 iodide ions. So if everything was carried down correctly, everything should still be balanced, and this is our ionic equation. The last part is the net ionic equation. Net ionic equation basically shows, well, what actually reacted, what actually changed in the reaction, because chemical reactions are all about change. If there is a change, you should be able to see it in the net ionic reaction. Anything that does not change, meaning it's the same on both sides of the equation. In basic algebra, you learn if you have the exact same thing on both sides of the equation, that cancels out, right? Same is true with chemistry. Notice I have two NO3-, two nitrates on this side of the equation that are aqueous. On this side of the equation, I have the exact same two nitrates that are still aqueous. In other words, the nitrate ion did not change. It stayed the same. Nothing about it reacted. That's what we call a spectator ion. Spectator ions are ions that are just in the background. They don't actually react in the reaction. And in the net ionic equation, we're going to ignore that. So I'm going to just mark through it real quick and say that we're canceling them out. The other ion in this equation that did not change was the sodium ion. That was the same on both sides. I'm going to cancel that too. Now, just a disclaimer here. You do not have to have spectator ions. Sometimes nothing cancels out, in which case the net ionic and the ionic will look exactly the same. That's fine. Likewise, sometimes when these two things react, nothing was a precipitant. Say, instead of making lead iodide, this made something that was also aqueous, and both your products were aqueous. In that case, everything would be a spectator, everything would cancel out, and in the end you would say that there was no reaction. But in this case, we did have a reaction because the lead did change. It went from being an ion to a compound, and the iodide did change. It went from being an ion to a compound, from aqueous to solid. So in the net ionic equation, we're going to write out everything that did not cancel. So that is the lead 2+ and the 2I-. And on the product side, that's the lead iodide. And this is our net ionic equation. So this is how to write a molecular, an ionic, and a net ionic equation, and this is for a precipitation reaction, where the two ionic compounds basically just switch partners, and then you determine if one of them was a solid at the end of the equation.